Okay, good morning. Let's start. And before we go into the nitty-gritty details of probabilistic modeling, something that I came across over the weekend. Maybe you've seen that, maybe not. I think I was aware of it, but not really or something. Anyway, there's the Alan Turing Institute in the UK, and you may think about the UK what you want, but it's fairly inspirational if you're an aspiring data scientist to see something like this. So it's kind of a nationwide institute that is all about data science and artificial intelligence. So it's if you want to know what can be done about data science on a national scale, and how data science, and actually I'm looking for this website where it says data science machine learning, what can be done and what is interesting and what you all do, and that this is actually a current topic. This is fairly inspiring. So it's a big website. It's of course a fancy website and with a lot of high quality bullshit on it, but it's also shows quite some scope to the whole data science thing, and it's really nice. So it was originally formed by like 7 universities in the UK: Oxford, Cambridge, UCL, and now there are more universities involved. It's really nice. Have a look around. It's fairly inspirational. Not like in Germany, where Peter Altmaier fällt von der Bühne auf dem Gipfel zur künstlichen Intelligenz. That's not that inspiring, but this is very inspiring. Anyway, have a look at that. Good. Then we would like to continue, of course, with the lecture. And let's see. First of all, are there questions left over from last session on random variable transformations? So, I mean, we're still, I guess, trying to get rid of the typos, but something kind of more on a broader scale that you would like to ask about, something, anything? Doesn't seem to be the case. Good. So then today is definitely the last session and section on probability theory. So these probabilistic foundations that we need to discuss. And from next time on, and maybe today, let's see how fast that goes, we will then start talking about frequentist statistics. Today, the aim is to discuss a number of things from probability theory that, for anyone who's done mathematical probability theory, you definitely will have come across. For everyone else, you will also have heard these things, maybe not the inequality, but definitely the limit stuff. And it's not like a coherent story, and it's not that much about data analysis, but it's a collection of important results that will be used downstream. So, for example, at one point we are going to discuss the Kramer-Rao bound for the variance of estimators, which tell us basically how good certain estimators are in terms of their variance, or how good they can be at most. And for this, we will need something called the correlation inequality. And so basically to understand where this is coming from. And the aim today is to establish a lot of these things that we will need later on. So on their own, these topics are a little bit tedious and mundane or something like that. But in the context of what is coming afterwards, they are actually, knowing about them actually makes understanding things that will be of interest and very important in data science later on possible. So the way actually I went about this lecture is that I, as you might have seen also from what is available, I first worked out things up to the last real thing of frequentist statistics, namely hypothesis testing. And I worked out this section of this lecture then last, because this is basically just collecting everything that will be of need later. And if you study in a way, I would also recommend going this way, because if you don't find yourself intrinsically interested in what we're doing today, then I would propose, if you study the study questions and so on, that you first skip section 5, do the stuff that is more interesting in terms of data analysis, but then you will always be kind of pointed to things in section 5, and then once you know where these pointers are and so on, then you might feel much more motivated to look into section 5, because, like I said, it's a lot of results that are important for later stuff, and in their own right, they are kind of interesting for people who are interested in these things. So that's kind of the intro. The current version of the slides online is kind of the stuff that I'm presenting, so it's building up. There will be once I've presented this, there will be the standard version online. This is where all of this is coming from. It has the same disclaimer. So also the disclaimer is that we are not wanting to, and we cannot afford to go into really details about all of these things. So our focus, like always, somewhat in this lecture is on the results. Sometimes here and there we look into proofs, mainly to understand where things are coming from, and if the proofs are kind of short. If there are long proofs, for example, today we discuss or we will cover central limit theorems. This is an elaborate proof, and it's very interesting and important for mathematicians and so on, but we just can't afford to go into that much detail. So the focus, like always in this course, will be on results and proofs only if they are quick and help us to understand what's going on. But again, we will not go into details about many things. And another thing is, this is basically put together from basically all of the books, because I always find in one of the books the explanation is most straightforward, and then I usually take this. So, but it also means that these things you find in all of the books that do statistical inference. Yeah. Good. The topics are expectation, variance, covariance, inequalities, and limits. And I think we just jump right in, and then we see what that is. And as promised, the next section then will be on statistics and finally data analysis. Expectation. Something that you've all seen before whenever you had some probability theory or statistics. So here a definition: the expected value or expectation of a random variable is defined as the integral of the values that the random variable can take, weighted by the probability mass that the values of these random variable take on. If the random variable is discrete, this amounts to multiplying each of the values that the random variable can take on by its associated probability mass. So who knows what the expected value of a fair dice is?
3.5.
Exactly. So if you basically weigh 1 to 6 by 1 over 6 and add them all together, you get 3.5. This is the expected value. From this example, you see that the expected value is not necessarily a value that the random variable actually can take on, because fair dice, if you model it discretely with discrete probabilities, will not take on the value 3.5. But that's about it, and so you can easily compute that in the discrete case. In the continuous case, it amounts to an integral where you multiply the values that the random variable can take on by its probability density function. This notation here you might find fairly explicable or whatever. So what is done here, and this is borrowing from the Wassermann, this would be if we would discuss the Lebesgue integral, then this would have some meaning, and then we would have one integral that we can always invoke irrespective of something whether it's discrete or continuous, and we would be able to show that, for example, for Lebesgue measure, this integral would correspond to this Riemann integral. Who has studied Lebesgue integrals? Okay, so you know what I mean, I guess. And this is basically going back to where we, when I first introduced kind of this measure theoretic approach, together with the Lebesgue integrals, they allow one language for the discrete and the continuous case. If you're not familiar with Lebesgue integrals, you can basically deal with sums in the finite case or series in the countable case, and deal with Riemann integrals in the continuous case. So these are the integrals that you know from school. And yeah, if you feel motivated, look into what is called the Lebesgue integral. It's actually not that hard, but one needs some technical things to introduce it, and we don't do that here. Yeah, there is always something about the existence of expected values. Expected values exists if they are essentially non-finite. So if we can compute a number, then we say the expected value exists. Intuitively, the expectation is a couple of things. So it's a one-number summary of a distribution. So if you have a Gaussian distribution, for example, with expectation parameter 5, and you can compute that the expectation then is 5, you can say, okay, this Gaussian distribution, we can summarize it with its expected value, which is 5. So 5 is in some way the most likely thing to arise. So it's a summary. Of course, always keep in mind that the expectation or the expected value is formed for a random variable. Yeah, so this is something very different from a sample mean. A sample mean you compute on observed data, so realizations of random variables. And expectation is a theoretical or analytical quantity that you compute on a theoretical entity or analytical entity, namely a random variable. So you can compute expectation as soon as you say, I have a random variable with this probability density function or this probability mass function in this outcome space. Then you can apply these sum or integral formulas, and you can compute the expectation, and you have a summary. Of course, if you, in terms of intuition and also with respect to the laws of large numbers that we will see later on, you can envision the expectation as something like a sample mean for very many samples. So if you think you have a random variable, you draw n numbers from it. So you get n realizations, you compute the sample mean, and now you increase the sample size ever more. Then in the long run you will approximate the expected value. Yeah, so the intuition that you can have also from an expectation is that kind of as a mean of the realizations, but always keep these two things nevertheless separated: expected value or expectation computed on a random variable, sample mean computed on a sample, and we will see more of this. Yeah, this is what I mentioned, that this Lebesgue integral serves as a summary notation for this, and we will not basically use this notation much more, so that you've just seen it. And this is what I said, that the formal basis for this is the Lebesgue integral. So that would be the definition. So then let's immediately look at an example. So if we, for example, have a Bernoulli distributed random variable, so x is distributed according to a Bernoulli distribution with parameter mu, then we can compute the expected value, and the expected value evaluates to mu. How do we get to that? Well, we need to apply the formula. We have a discrete random variable which can take on the values 0 and 1. So the x can take on the values 0 and 1. And each of these x's needs to be weighted by its associated probability mass. For the probability mass, you remember that we've seen the definition of the Bernoulli distribution as mu to the power of x times 1 minus mu to the power of 1 minus x. If we then substitute this in this formula, we have to sum over 0 and 1. So we have 0 times the associated probability mass, which gives us mu to the power of 0 and 1 minus then we have 1 times mu to the power of 1 and 1 minus to the power of 1 minus 1. Of course, this term goes away because this is 0, and we are left with this. And to the power of 0 evaluates to 1, so we end up with mu. Yeah, so it's fairly straightforward, of course, this calculation, but what I want to stress is that the expected value you calculate based on the sum or the integral formula for the random variable of interest. Yeah? It's not a sample mean or something like that. Yeah? Second example, Gaussian. This is actually one of the last things I put in, because of course I assume that you all know that if you have a normally distributed random variable with expectation parameter mu and variance parameter sigma square, you know that the expectation of this Gaussian random variable is mu. However, deriving deriving that the parameter mu here is actually the expectation of a Gaussian random variable is not completely trivial. One way to do this is with moment generating functions. Does anyone know what moment generating functions are? No? Doesn't matter, we don't cover them anyway. There is a whole theory how you can basically get from probability density functions to moment generating functions, and then you can compute moments somewhat straightforwardly. This is done without moment generating functions. Basically what we have to do, of course, is to compute this integral here. So we have to integrate the Gaussian density multiplied by the value x, and integrate this over all of r, or from minus infinity to plus infinity, kind of over r. And this is then a problem in integration, right? So we are in calculus, we need to compute integrals. And this so I looked a little bit around this. I found on this proof wiki site. There will, when we talk about the variance, there will be a link to it, so you can also see that. The way it's done here is it basically rests on appreciating that integrating x times x minus x squared equals 0, and that this here, the Gaussian integral, evaluates to the square root of pi. These are also not trivial things, right? So to show that this is pi, square root of pi, for example, this one can do via polar coordinates. This one can do based on the theory of odd and even functions. But so here I just assume that this is given. And then the proof or the derivation that is left after basically saying, okay, the difficult stuff that's already solved, then this works by basically using a transformation. So basically using a variable transformation and getting this essentially to transforming it and accounting for the fact that this is a probability density, then separating out the integral, and then using these solutions. So have a look at it. We don't need to go into details about this. What I want you to appreciate is that computing expectations and expected values is not necessarily trivial. Yeah? So it's not always as simple as this, and even for the Gaussian, it's not completely trivial. The good thing is if you have some kind of distribution that you're currently interested in, so for example, beta distribution, gamma distribution, or whatever you want to do, exponential distribution, Of course, the expected values for these have been computed a long time ago, and it might actually be quite hard to figure out when they were first computed, but they are known. So if you, for example, go to Wikipedia and you look at how these distributions are discussed, you will always find the expected value and the variance and so on. So these are kind of academic exercises. It's not that most of the time you actually need to compute them yourself, but if you're looking into it, it might not be completely trivial. Yeah. This about like how expected values and are computed. The nice thing often in probabilistic models, you will have actually some more, or also in statistics and so on, compute expectations when you put together random variables and so on. And there are some properties of expectations which are helpful and can help a lot with that. So one thing is that expectations are linear, so the expected value of this linear combination of random variables, so the AI are constants, these are random variables, can be computed by the sum of or the linear combination of the expected values of the xi. So you can basically put the if you view the e here as an operator, you can basically put the operator inside this sum. Under independence and only under independence, if the x1 to xn are independent, then the product of these xi evaluates as the product of the expected values. And again, this can be helpful. For these properties, so essentially, of course, these properties follow from the properties of Riemann integrals or sums, and in this case, in addition, the independence. The proofs of these will be discussed in the Übung, so I finally also uploaded the exercises for section 5, and there we will briefly go over these proofs. You find them in the books. What these proofs help you, of course, is to become familiar with the definition, and we will then look at this a little bit more. That was already expectation. That was quick. Questions about expected values right now? No. Good. If there's expectation, there's also, of course, always variance. And the expected value being a one number summary of a distribution that basically is a measure of the central tendency. Then variance is, of course, a measure of the dispersion or variability or spread of the random variable. And the variance of a random variable can be or is defined in terms of expectations. So if you know what an expectation is, then you can of course compute the variance. And it's defined as the expected value of the square of the deviation of the random variable from its expected value, and again assuming that these are finite numbers. The standard deviation being defined as the square root of the variance, with the aim of having a measure of spread that is at the same scale as the random variable itself. Again, these are analytical quantities. This doesn't refer to a sample variance. This doesn't refer to a sample standard deviation. These are things that you can evaluate and calculate or compute as soon as you defined your random variable, and of course you computed the expected value of the random variable because you need it. And if you have computed the expected value of the random variable, you can then write down this and compute an expectation again. It measures the spread of a distribution, so a higher variance, higher spread. The square is basically, I think most of you are familiar why you need the square, because you all computed sample standard deviations. Here on the square, you can basically, if you would just apply the expectation operator to x minus its expected value, the expected value here, so this, if you compute the expected value of an expected value, you just get the expected value. The reason for that is you can either view this, if you look, for example, into the de Groot and Scherbisch book, they discuss how expected values work on linear affine functions, where you have these constants in there. The other way you can look at it is that the expected value here is, of course, a number. So you compute a number, it's not a random variable anymore, and the expected value of a constant is just that constant, because it doesn't vary. So that's kind of an intuitive way to think about it. And then if you would just do this, you would have the expected value of x minus the expected value of the expected value, which is just the expected value, and you would get 0. This is the same thing as you know from computing sample standard deviations. However, one thing that I also want to stress is that variance is by no means the only way to evaluate the spread of distributions. So another thing that you could, of course, do is to use absolute values. And another thing that I mentioned here, without discussing what that is entropy. So we will have to, latest when we talk about variational base, we will have to also introduce entropy. But entropy is also a measure of the variance of a distribution. So there's not only the variance as a measure of the spread of a distribution. It's one specific measure. Yeah. For the Bernoulli distribution, again, one can quite straightforwardly compute the variance. It turns out to be mu times 1 minus mu, which also shows you, if you're coming from the Gaussian distribution, this is sometimes maybe a little bit, because you've seen Gaussian so much that everybody thinks that all distribution should have a variance parameter, but most of the time, actually, the probability distribution don't have a variance parameter, but the variance of the distribution can be usually calculated based on the parameters of the distribution. So in this case, for Bernoulli random variable, there's of course only one parameter, this mu, which is the probability to observe a 1, and the variance you can compute by multiplying mu times 1 minus mu. Yeah. So you can also think about because mu can vary between 0 and 1, so you can, by thinking about this formula, you can also think when a Bernoulli random variable has most variance and when its variance is fairly low. Yeah, so this basically then showing how this would be evaluated. So here we have the expected value already. So we have, because we evaluated that previously, so we have to do x minus the expected value and square this and compute the expected value. That means if we want to compute this expected value, we have to again sum over the values that the random variable can take on. And now consider not the just x, but the different values that the random variable can take on, minus mu, and square that. That means we have to sum over 0 and 1, and then plugging 0 and 1 in here gives this term and this term. And then there are some simplifications, Wulle, and in the end you get to this. Yeah? So you can go step by step over what's happening there, but this is then the result. This is me yesterday, because at one point, so my energy was dropping, and then I thought, well, if I copy this, there will be more typos in me copying this and trying to explain this, then it helps. Yeah, so maybe we can briefly look at it. So the proof is fairly similar to the so of course what it shows, sorry I didn't say that, what it shows is that the Gaussian, the variance of a Gaussian is corresponds to the variance parameter, and it again uses these results that we've seen, and then in addition, and this is why I really didn't want to start working on it, it also uses integration by parts. And so if one would really do that foundational-wise, then we won't have to discuss also that and so on. So there are proofs, there are also moment-generating functions. The proofs are, again, not trivial, of course, because we are now dealing with the variance, which is in its definition already a little bit more complex. This derivation is also a little bit more complex. But of course, the result is well known to you, that the variance of a Gaussian random variable corresponds to its variance parameter. But this is also why I'm always calling these things expectation parameter and variance parameter, to distinguish them from the variance and the expectation. Something that is quite helpful for variances, when computing variances. So when I did a lot of probabilistic modeling, for example, in variational inference, I constantly came across that because it allows you to, for example, compute the expectation of squares of random variable, or compute variances without having to do these x minus the expectation. And this was referred to as the variance translation theorem. So the variance of x is equal to the expected value of x square minus the expected value of x square. So you see the difference. This is fairly easy to establish. So this is the definition of the variance. Then if you use the binomial formula, what's the English term for that? Binomial formula, binomische Formel. You know that if you have something like this in brackets with a square, you get x squared minus 2 plus this square. Then you apply the expectation parameter, and again you here have a random variable for which you evaluate the expected value, and the expected value, so basically you can also view the expected value in front of this 2xex, and then you can take the 2 out because it's a constant. You can take the ex out, and then you're just left with the expected value of x. So you have 2 expected value of x times the expected value of x. And this is 2x squared, and then you have expected value of x squared minus 2 times the expected value of x squared, so you're left with 1 expected value of x squared. And that's the translation theorem. It's, if you, for example, in some case know what the expectation of the square is, this is very helpful. And like I said, it's also very helpful if you, for example, want to compute the expected value of x squared, because then you just need to add the variance of x and the expected value of x and square that. So this is actually, that's often useful. More properties on the variance, which again, of course, are discussed in depth in the books, and we will also see their derivations in the Übung. One thing, if you have a random variable x and you pre-multiply it with a constant and you add a constant to it, of course the constant b doesn't have any variance, so it doesn't show up anymore, and the a, and this is something, you can always look again into the proof, but it's also something that doesn't hurt to learn by heart, and without asking why, you have to square the a. So if you have the variance of 2 times x, then that's 4 times the variance of x. And this generalizes to n this generalizes to n values if these are independent variables. If these are not independent, we will actually see that the covariance of these variables comes in. But for independent random variables, of course, the covariances between the individual random variables are 0. So here you don't see any covariances, and you because the assumption is that the x1 to xn are independent, and you get out this formula. Again, we will discuss the proof of these in the Übung, which again help you, if you go over the proofs, to become familiar of how variances are evaluated. So these proofs are actually helpful if you want to internalize the notion of expectations and variances. Good. Third topic, or questions about variance right now. Yep.
I was just wondering, could you give a working definition for the linear affine functions?
Linear affine function, yeah, the function that is here. So it's a function, so the x is the argument, and it's multiplied by some value, and with this alone it would be a linear function because it's going through 0. And if you add a constant to it, and if b is not 0, then it's only linear affine because it's not going through 0. So that's actually this is a linear affine function. Yeah. Yeah. Any other questions? No. Good. Covariance. And as you have figured, I didn't list variance here. I've went through iterations. So also I had co in brackets. Maybe it would also be nice to say expectation variance covariance inequality limits, but I think it's very long. Anyway, the covariance of a random variable with itself is of course the variance. Hence, variance you can view as a special case of covariance. So this is why I now remove it. But it's just madness in my head. Yeah. So the definition of covariance between two random variables, I guess you've also seen that before. If not, you've definitely computed correlation coefficients, and there you do something fairly similar. So the covariance of two random variables with finite expectation is defined as the expected value of x minus its expected value times y minus its expected value. What you should, so if you ever thought a little bit about the correlation coefficient, you will have figured that what this kind of measure this measure measures is, or let's say like this measure gets large if so large in a positive sense, if the random variables deviate similarly from their expectations. So let's say whenever x is above its expected value, so it's something positive, and y is also above its expected value, then you would multiply two positive numbers, you get a positive number. If x is often below its expected value, so negative, below, so that you get something negative, and y is also negative. If you multiply these two negative numbers, then you would also get positive covariance. And then of course you can also have the case that one of them is always positive, so above its expected value, and the other one is always and very often below its expected value. Then you get a negative covariation. So these things can happen, and and if these kind of co-occurrences, that x is above its expected value and y is above expected value, if they don't occur regularly, so that x is sometimes above its expected value and sometimes below its expected value when y is above its expected value, and all the other different permutations, then you wouldn't have much of covariance. The correlation then being a standardized measure of that, so rho here for the correlation, and being computed as the covariance divided by the square root of the individual variances. And we will have a look at this a little bit more when we talk about the correlation inequality in a second. So we will see that this correlation varies between -1 and 1. Again, try to distinguish in your head the notion of a correlation of random variables from the notion of a correlation coefficient that you compute based on data. Of course, the formulas are very similar, but a correlation coefficient you compute based on observed data or realizations of random variables and based on these sum formulas, whereas a correlation you compute analytically based on the definition of the random variables x and y by basically first evaluating their covariance and their respective variances. Yeah. So again, correlation and covariance, as you see, are not the things that you compute on data. These would be correlation coefficients and sample covariances. One thing that is, I will not discuss in detail, but something that you should internalize actually, would be nice if I finally put that in, because that's also something that I always wanted to put into SCAN. Correlation is a measure of linear dependence. So if x is a linear function of y, then the correlation is very positive, so roughly around 1, or negative depending on the a parameter, for example, so the slope parameter. So you can have stochastic dependencies that are not picked up by correlation. Yeah, it would be nice to, at one point, so who knows that? Or does everyone knows? Who knows that correlation measures linear dependence? 2 people. So maybe this should then be, at one point, be taught more, because it's very important, but it's always something that I think everybody knows anyway, so I don't have to make a fuss about it, and it's a little bit boring, but yeah. Anyway, definitely it's in the book. You can reformulate a correlation and simple linear regression into one another. I always thought this is something that you learn in undergrad statistics.
Not under the term linear dependence, but we know that correlations are just linear relationships. It's pretty much the same.
That's the same thing. Good, so you know it. Good. Keep that in mind, and if you want to see proofs for this linear dependence thing, look into the De Groot and Shervish. If you want a measure for nonlinear stochastic dependencies, mutual information is a measure that measures or that accounts for all forms of linear dependence, not necessarily linear dependencies. As for the variance, there is a covariance translation theorem for covariances, which looks fairly similar to what we've seen for the variance. So if you don't want to do this thing with the minus and multiplying and so on, you can also evaluate the covariance between two random variables by evaluating the expected value of x times y and subtract from it the product of the expected value of x with the expected value of y. This is also fairly straightforward to see. The logic is the same. So you apply the expected value to these kind of terms that are mixtures between the random variable and the expected value. And then you have two of them, and they cancel each other out, and you are left with one of them. Yeah, and again, this helps if evaluating the expected value of the product of x and y is easy. If y equals x, then of course we are back at our earlier variance translation theorem. So you have here x squared, and here you have the square of the expected value of x. So it's kind of a generalization, if you want, of the variance translation theorem. What we've seen previously, was that the expected value of a product for independent random variables x and y is given by the product of the expectations of x and y. So we've already established this previously. Yeah. So for independent random variables, we've seen this. I mean, we established it by saying the proof will be given in the Übung. At least we made it. Yeah. We establish it virtually, based on this, it then follows that the covariance between independent random variables is 0, because if this here is the same as this, then of course you get 0. Just links this back to this product rule for expectations. Now with the covariance, one can say a little bit more about the variances of sums and differences of random variables that are not necessarily independent. So we've seen this for independent ones. There, this was 0, and there was just the variance of x plus the variance of y. In general, the covariance has to be taken into account when computing the variance of sums and differences of random variables, which can also be generalized here. We've seen this before for independent random variables. If they're not independent, we have to account for basically all pairwise covariances. Proofs of these properties are discussed in the Übung. So this will be, there are 3 exercises for that, and one will be on expectations, the other will be on variances, and the last one will be here on covariances. So if you wonder where these things are coming from, we will see where they are coming from. Well, good, and this is a good time for a break. Any questions? So these are really just basic facts about the definition of expectation, covariance, and variance. There's more to know about these things. So if you read the De Groot and Scherwisch, this is a fairly comprehensive account for all kind of things that are important in applications of these concepts. Always keep in mind that expectation, variance, and covariance are analytical properties of random variables. They are not description of the variability of some data. Yeah? We will talk about data when we talk about statistics. Right now we're talking about probability theory for the last time in this course. Good, then let's have a break, 15 minutes, and then I'll continue 11:15. Okay, and then as the really last part in pure probability theory, some inequalities and some limits. First about these inequalities. So we will discuss, I think, 4 or 5 or so. Markov, Chebyshev, Jensen, correlation, and one I'm forgetting. So per se, and the way I present them now, it's kind of so what. But again, later on, for example, if we talk about the quality of estimators, we will relate this back, for example, to the correlation inequality. Or when we talk about variational inference and why this works and why you can approximate the evidence with the variation of free energy and so on, this will be essentially because Jensen's inequality applies. So these are kind of very foundational things that are more or less tricky to prove, often actually less tricky, and they basically can then be used in a data analytical context and are helpful. So please see them in this way and not like so because per se you might find that they are not that interesting, and you wouldn't know how to use them for anything sensible in terms of data analysis. But as I said, later on we will, in some proofs, refer to them, so then you will know what we mean. Good. So a couple of these inequalities. So first, Markov inequality. So assume that x is a random variable with a probability of being equal or larger than 0 being 1. So x doesn't come out negative. Then it holds for all x that the probability that the random variable x is larger than this small x is smaller than the expected value of x divided by this value x. Yeah. So essentially, if you want to make some use of this, you can substitute some value for x, for example 2. You can compute the expected value of the random variable, and then this inequality, that the probability that x is larger or equal than 2 is always smaller than the expected value of x divided by 2. That's actually relatively straightforward to establish. So I wrote it down for the continuous case. So if you compute the expected value of a continuous random variable, then of course this is given by the integral over the values of the random variable multiplied by the probability density. And you can of course split this up from -infinity to x, and then from x to plus infinity. Now we assume that x takes on values only 0 or larger than 0. First of all, if we do away with this term, then of course something is missing, and we have the expected value of x being larger or equal than this. Then we account for the fact that this, of course, this c goes to infinity, and if we keep it at this lower bound, then we are again smaller or equal then we can take out the x and have just this integral, and this is of course the exceedance probability of x being larger than small x. And then if we divide by x, we get to this inequality. So what this Markov inequality does, it relates this exceedance probabilities, so the complementary probabilities of cumulative probability mass functions, to expectations. It's just this inequality. An example here, if you have a random variable with expectation 1, then the probability that x takes on values larger or equal to 100 is always smaller or equal than 0.01. Yeah? So it relates kind of this expected value to probabilities of extreme values. Why is it interesting? Mainly because it can be used to show the Chebyshev inequality, which is a statement involving the variance of a random variable, and again some kind of strong deviations. So what the Chebyshev inequality says is that if x is a random variable and has a variance x, has a variance vx, then the probability for x to deviate from its expected value in an absolute sense, so here you have the absolute value of x minus its expected value, the probability for this to be larger than some value x is always smaller than or equal to the variance of x divided by x squared. And so essentially this relates the variance. So if you have high variance, then of course this you can go a little bit higher with this small x. If you have very little variance, then it's more unlikely. So you link how probable is that the random variable comes out very far from its expected value to the variance of the random variable. Yeah? And this can be shown fairly straightforwardly with the Markov inequality. Actually, I realized that by preparing this slides for the course, that this kind of equivalence, that if a square is larger or equal than b square, that this is equivalent to the absolute value of a being larger or equal to b. This is behind a lot of things. This was also the thing that we discussed last time. I originally set up a little bit of a proof in one direction for that, but then I deleted this again because it was only in one direction and then was all about this thing. So if you don't feel quite comfortable with this, I think it's something that it's a typical kind of inequality analysis kind of proofs. Play it through, you will see that it's true. And play it through in this way and the other way. Maybe at one point I get to write that down. But if you appreciate that this is true, then you can essentially just apply the Markov inequality by now taking x square and plugging y, the expected value of y and x square, into the Markov inequality, which we've already proven. Then if you substitute again for y, sorry, I didn't say that. So you define y as x minus the expected value of x. And then you use the Markov inequality for y and x square. Yeah, so you just write down the Markov inequality for y and x square. Then you substitute again what y was. I'm not quite happy with this. What is going x square? I think I missed. Sorry. There's a typo. This is the typo. This needs to be. Oops, that's my. There we go. So as you can see here, I'm substituting y, but y needs to be defined as this, because I also substitute that here. So y is defined as x minus the expected value of x square. Then you just set up the Markov inequality here, and then it's substituted, but now correctly based on the definition of y, which then leads to this a square larger or equal to b square in this probability statement here, and you have the expected value of y, and the expected value of y is x minus ex square, because that's how it's defined correctly. And then you can transfer this statement by this into this, which is already this, and of course the expected value of this is the variance of x. And then you have basically used the Markov inequality and the definition of y as the square of x minus ex to derive the Cauchy-Schwarz inequality. Again, something that we will use later. And yeah, it relates deviations from expectations to variances. I already said that. This is somewhat interesting. So if you think about the probability that the absolute value of the difference between x and its expected value is larger than 3 standard deviations. So remember, standard deviation is the square root of the variance of x. Then the Cauchy-Schwarz inequality says that this is the variance of x divided by x square. X square here is 3, and if you square this, you of course get the variance of x, and you get 9. Then you can divide the variance of x by the variance of x, so the variance of x cancels out, and you actually get a number. And this says that the probability that x deviates from expected value by more than 3 standard deviations is always smaller or equal to 1 over 9. Awesome mathematics. Sorry. Yeah. So these were these two inequalities that essentially relate deviations or probabilities for random variables to take on extreme values to expectations and variances. Jensen's inequality is actually something different and is talking about applying functions to random variables and then making statements about the expected value. And so, as you see, these inequalities are not really related. So the Markov and Chebyshev go together, and we will also see the correlation that link. So, so in a way, if you want some structure to these inequalities, Markov and Chebyshev are about probabilities. So they relate probabilities to expected values and variances. Jensen's inequality is about expected values, and Cauchy-Schwarz and then correlation inequality is about correlations, yeah, and covariances. So right now we're going from probabilities, Markov and Chebyshev, to an inequality about expected values. And the point of Jensen's inequality is that if you apply a concave or convex function to a random variable, then the expected value of this concave or convex transformation of the random variable behaves in a kind of predictable manner to the value of this function at the location of the expected value. Yeah. So more explicitly, if you have a convex function, that is a function for which, let's draw it because that's easier to see. So a convex function is of course a function for which the graph, so the graph here being called G, lies below the straight line. So this here on the right side, that's the straight line that I drawn here, and the graph, a convex function, the graph of a convex function always lies below that. So if you're not quite clear about convex and concave functions, clarify these definitions for you, because you have to think about this convex combination between these points. For convex functions, the expected value of the convex transformation of x is always larger or equal than the convex transformation of the expected value. For concave functions, and this will be highly important for variational inference, because the logarithm is a concave function, the reverse holds true. So in this case, oops, sorry, no, that was wrong. I was thinking about the tangent line in the proof, but of course for a concave function, these straight lines lie below the graph. Then the expected value of the convex transformation of x is smaller or equal than g, the transformation of the expected value. And this is actually what's behind variational inference. So if you want to understand variational base, if you understand Jensen's inequality, you already understood most of variational base. But we will get to that. Yeah, and as I said, the logarithm is a typical example for that. This is also not that tricky to prove, so I do it here for the concave case, and the reasoning is essentially, if I make a little drawing, so let's call this Ex, and then have a tangent line here, not the most beautiful tangent line, something like this, and there it hits it. So if and this point here is supposed to be g of Ex, it's this point here with the x-axis, y-axis. This tangent line you can, of course, again describe by a linear affine function with x being ax plus b from a for some a and b. Because it's tangent line at the location ex, it has the same value as gx. So maybe make this more explicit. This is g, and this is f, and because we have this concave function and this tangent line, the concave function is always below the tangent line. Yeah, so we're now not talking about the definition of concave function, but about this with the tangent. Then we can basically think about it. So the expected value of gx is smaller or equal than the expected value of ax plus b, because this tangent line is always above gx, as you can see here. Then we can apply the expected value operator. So basically b remains b because the expected value of a constant is a constant, and this a gets in front of it. This is of course the same thing as the value of the tangent line f at the location ex, and because it's the tangent line, this is equal to g e of x. Yeah? So this establishes Jensen's inequality kind of with some geometric intuition. And of course you can reverse this whole thing for the convex case. No? But this is what Jensen's inequality is about. We will see Jensen's inequality at latest. I think we see it earlier, but we will see it at latest when we talk about variational inference, and then the whole magic of variational inference will be there.
Is there a difference between a linear function and a linear affine function?
Mm-hmm. The difference is in if you do it in R2 essentially. A linear function is of course defined as can do it like this. That's the definition of a linear function, and a linear affine. And if you study linear function, you will see that they always go through zero. So linear functions always map 0 onto 0. Linear affine functions in the two-dimensional case have this general form of fx. It's a little bit hard to draw on this. Sorry, it's a little bit messy. This form, and if b is non-zero, so for example you have some function like 2x plus 1. If you check these definitions of a linear functions for this thing, you will find that they don't hold. These functions that basically kind of are linear function with some offset, they're called linear affine functions. Okay? Good. That was Jensen's inequality. Any questions about Jensen's inequality besides the fact that the real power of it will only be seen later? No, I mean, what should one ask? Cauchy-Schwarz inequality, mainly of interest because it directly relates to the correlation inequality, which directly relates to the Cramer-Rao bound, which will be an awesome result in estimator quality. So Cauchy-Schwarz inequality, you might have seen that name in other mathematical studies, for example in linear algebra. It's easy to confuse this, or at least I tend to confuse Cauchy-Schwarz inequality with triangle inequality. It's not the same thing, but it's somewhat similar. So for example in linear algebra and scalar products, you would write it like that. So if you have come across the term Cauchy-Schwarz inequality in different settings, it's essentially the same thing, but in this case for random variables. What it says is that if the expectation of, this is of course wrong, that should be E x y, not with a comma. If this expectation exists, then the square of this expectation of the random variable x times the random variable y is smaller or equal to the expectation of x squared times the expectation of y squared. And this is a little bit more elaborate to show. So there is a full proof, of course, of all of these. There are proofs in mainly the de Groot book. So I think the Wasserman doesn't prove anything. He just writes all of the inequalities down. The Casella also proves them. The Casella is sometimes a little bit more straightforward, I think, in terms of the proofs. The de Groot is a little bit more comprehensive, but then sometimes a little bit less straightforward in terms of the proofs. Yeah. I wrote it down based on what I saw yesterday. Have a look at it. We don't have to go over it. It essentially rests again on our absolute value smaller than some value with the a square smaller than b square thing, and writing things out explicitly is here. Have a look at it. It's the main relevance of the Cauchy-Schwarz inequality here is that it directly relates to the correlation inequality. So the correlation inequality you can straightforwardly derive from the Cauchy-Schwarz inequality. Schwarz, because I'm so American, I cannot say Schwarz anymore. So the correlation inequality is something that we will need later on, and that is also interesting in its own right, is the statement that the correlation, the square of the correlation, which is from the definition, the square of the covariance divided by the variance of x times the variance of y. So remember that the correlation itself was defined as the covariance without a square divided by the square root of the variance of x times the square root of the variance of y. That's the correlation, but the square of the correlation is smaller or equal to 1. And how can this be shown? Well, of course, it can be shown with the Cauchy-Schwarz inequality. So if we say, okay, we believe that the Cauchy-Schwarz inequality holds, because we worked through the proof in the de Groot, then if we define the first random variable in the Cauchy-Schwarz inequality as x minus its expected value and the second one as y minus its expected value, then we are essentially already there. So here we would have the expected value of this product, which is of course the covariance. We have the square, so we have the square here, and here we would have the expected value of this and the expected value of this, and Cauchy-Schwarz says that this is smaller, so here we have the variances, and then we just divide by the variance of x times the variance of y. So on the right side we get a 1, and on the left side we get this squared covariance divided by the variances. And then we can again use our favorite inequality equivalence, that if the square is smaller than or 1, then the absolute value of the correlation is smaller than or equal to 1, which means that the correlation is bounded by -1 and 1. Yeah, it's the correlation inequality that is of main interest for later stuff. Again, in terms of the hierarchy, correlation inequality being a straightforward consequence of Cauchy-Schwarz inequality, Cauchy-Schwarz inequality not being that straightforward to show. Good, so these were all inequalities that we need. So if you try to memorize these inequalities, structure them again in terms of inequalities about probabilities, Markov inequalities about expected value, Jensen, inequalities about variances, correlation inequality, and correlation inequality being linked to, although it's not really about variances, the Cauchy-Schwarz inequality. And again, we will need them later on. Good. Then something about limits. And this now you can view from two perspectives. So you can either view it fairly pragmatically in terms of, okay, this is what I put on this slide. Law of large numbers essentially says that the sample mean approximate the expected value. This is the main thing that the law of large number says. So if you go to very large sample sizes and you compute an expected, if you go to very large sample sizes and you compute the sample mean, then the sample mean very well approximates or estimates, if you want, the expected value of this random variable. And the central limit theorem basically is saying that if you add together many random variables and look at the distribution of this sum will be normally distributed. And I think everybody has heard this before. So law of large numbers saying that sample means approximate expected values. Central limit theorem saying that if you add together many random things, you get a Gaussian distribution or normal distribution, which of course is a good justification for using Gaussian errors in many settings. So this is essentially what these theorems say. And that's kind of the pragmatic view and something that you should definitely know. One can, of course, go more mathematical about them. And then talking about these limit statements, talk in some depth about also the convergence properties of random variables. Remember, random variables are functions, so they map values of the outcome space onto real numbers. And if you talk about convergence of random variables, you hence talk about the convergence of functions. And you might remember things like, or who remembers the difference between uniform and pointwise convergence of functions? Some analysis thing. Who has heard that there is something called pointwise convergence of functions and there's something like uniform convergence of functions? Has anyone heard that? No? So, I mean, it's typically you encounter this in analysis once you discussed a convergence of sequences and series. Once you have discussed that, then the next thing is to talk about sequences of functions. And there you encounter these concepts of pointwise and uniform convergence, where actually uniform convergence is the stronger thing, and pointwise convergence just means for all of these values. Thing is, this, so talking about convergence of random variables rests on convergence of functions. So if you don't feel quite happy about these convergence properties, then maybe it's because you don't feel quite happy about convergence of functions. You don't feel quite happy about convergence of functions. That might be because you don't feel quite happy about convergence of sequences and series. So it can be a little bit mathematically challenging. On the other hand, and detailed. On the other hand, the intuitions of what is happening is just this. So feel free to dive into these theorems and the underlying convergence theory in terms of convergence and probability, convergence in distribution, convergence in distribution probability. I'm forgetting something. I'm almost sure convergence. Feel free to dive in as deep as you want. But don't forget that in the end, these things that are on this overview slide are the bottom line. Don't know what to say about this. So we first want to discuss the weak and the strong law of large numbers. So both law of large numbers say that if you increase the sample size and compute the sample mean, then you approximate the expected value of a random variable quite well. that's what both the strong law and the weak law, or the weak law and the strong law of large numbers say. The differences in terms of these weak and strong form refers to the convergence type that is considered. And we will come back to convergences when we discuss estimator properties and the large sample properties. So we will be very interested in what happens if we have a maximum likelihood estimator and we have a very large sample size. What can we say about the properties of the maximum likelihood estimator? So we will get often back to convergences. So try to appreciate them or get into them from now on. The first thing to go about these convergence types is just to memorize their definitions and leave it at that, and then try to understand a little bit more what this means, and then maybe relate it to function convergence and so on. But an important thing about these convergent types is also just because there are essentially 4 different forms to kind of associate with the name, associate the definition, and then you feel, or at least I feel a little bit as if I understood what's going on. So anyway, that's what I recommend. So for discussing the law of large numbers, we need convergence and probability and almost sure convergence. So convergence and probability is the following concept. There we already have a sequence x1, x2 of random variables converges to a random variable x in probability, written as xn with an arrow with a p above it to x, if for epsilon larger than 0, and epsilon being, of course, can be very small, the limit of the probabilities for the absolute value of the deviation between xn and x being larger than 0, being larger than epsilon is 0. Yeah. So one has to think about these definitions a little bit. So first of all, what would be an applied case? Well, an applied case would be that we have random variables that correspond to sample means, and a random variable 1 would be a random variable that is based on 1 realization. That would be x1. x2 would be the sample mean based on 2 observations, and you can think about computing sample means for ever more realizations, forever increasing sample sizes. And then another random variable could be a constant. So actually in statistics we will mainly be mainly interested in convergence to constants that would be a constant is of course a constant random variable, so one can in general formulate these convergence concepts in terms of convergence to random variables, but they can of course also be constants. Then what this says, so what it's talking about is the probability for the deviation of a random variable n from such a constant or another random variable being larger than some epsilon, and this epsilon being arbitrarily small. Yeah, so you always should think in terms of you can make this epsilon very, very small. It's still larger than 0, but you can make it very, very small. And if you keep increasing the sample size, then the probability that this absolute that this deviation of this random variable xn from x will be larger than epsilon, where epsilon is very, very small, is 0 or goes to 0. So here one verbalization of this. So there we also have the xn missing. This means that the probability that xn lies outside the random interval x minus epsilon, x plus epsilon, so x being the thing that is being converged to, no matter how small this interval may be, because this epsilon can be very small, approaches 0 as n goes to infinity. Now, If we think about a constant here, this means that the probability distribution of xi becomes increasingly concentrated around x as n goes to infinity, because the probability that xn deviates a lot from x goes to 0. Yeah? That's convergence and probability. And if one talks about now the weak law of large numbers, then the weak law of large numbers is just the statement that if we have a random sample from a distribution with expectation mu, so think again that by random samples we always mean independent and identical samples. So if we sample some distribution n times, and we compute the sample mean, that is, we sum together all the random variables and divide by the number of random variables. Of course, our sample mean is also a random variable, because these are all random variables, and hence we also get a random variable out. Then this sample mean converges to mu, which is the true expectation of this distribution, of which all of these x1 to xn are samples. Then xn converges to mu in probability. That means the probability that the sample mean deviates a lot from or deviates arbitrarily little, that's a different way to say, the probability that the sample mean deviates arbitrarily little from mu goes to 0 as the sample size gets very large. Yeah. Here's verbalization, finally with some n, that there's a high probability that the sample mean is close to the expectations of the xi if the sample size n is large. Yeah. Again, bottom line is it just says sample mean approximates expectation well. The question is, what does that mean exactly? And this is in the weak law of large numbers. This is stated in terms of convergence in probability. The strong law of large numbers, I briefly jump forward to the strong law of large numbers, says that if these random variables again denote a random sample from a distribution with expectation mu, again we have the sample mean, then the sample mean converges almost surely to mu. So we use a different concept of convergence, and also this can be shown. Again, what I didn't do here, of course, is to provide a proof of this. Yeah? This is the statement, this is the theorem. What would naturally follow would be a proof of this theorem, which I think involves Chebyshev's inequality. Proof is not here. Proof is omitted. Proof you can read up in the Degroote. Same for the strong law of large numbers. Again, one would have to prove this now based on this other convergence concept of almost sure convergence, which I will not discuss now because we're running a little bit out of time. Almost sure convergence is related to pointwise convergence of function sequences, and a big difference is here that actually the limit is inside the probability and the probability is 1. So it's just a different way of saying that something converges to something. Yeah? Again, bottom line of both the strong and the weak law is the sample mean for large samples becomes more and more equal to the expected value. Finally, central limit theorems in 5 minutes. The central limit theorems basically saying that if you add up a lot of random variables, something normally distributed comes out. They use the notion of convergence and distribution. And of course, there's also an n missing because all of these were copy-pasted. Convergence and distribution is actually a statement about cumulative density functions. So this statement is about that the limit of the CDFs of the random variables xn, they go to the CDF of the random variable x. Yeah. So this is now not talking about probabilities or the limit of probabilities, but it's talking about the limit of cumulative density or cumulative distribution functions. Yeah. And then one can study, and you will find that in the books, you can study the relationships between these convergence types. And the thing is that almost surely convergence is the strongest form, and it implies convergence and probability, and it also implies convergence and distribution. That's awesome. Now, with the notion of convergence and distribution, one can actually state the central limit theorem, and then, of course, also needs to prove it. And here are two versions of the central limit theorem. They are discussed in the root book, and yeah, it's just interesting to know because the central limit theorem is often invoked. So people often say, yeah, because of the central limit theorem, we can use the Gaussian, but it's also often not explicitly stated what do we mean by the central limit theorem. And what I like here is that there are these two statements of the central limit theorem without proofs, but at least we have kind of precise statements. And there are two forms, and one is kind of the weaker form. So the first form is the Lindenberg and Levy form, which assumes that we have independent and identically distributed random variables. Yeah? So that's the independence is also in the Lyapunov form that we'll see in a second, but the identical distribution is not in the Lyapunov form. So here, this would be the case. We have contributions to something that are all identical. If we have this, then the sample mean minus the expectation of this distribution for which these are all samples divided by the standard deviation. So sigma square in this case has nothing to do with the Gaussian, but it's a symbol for the variance. Maybe I should write this a little bit more explicit here, because this is now, we are not talking about Gaussian distributions here, we're just talking about a variance. And in this case, the standard deviation divided by the square root of the number. This probability to be smaller than x in the limit approaches the CDF of the standard normal distribution. Yeah? So what this says is if you have more and more random variables which are independent and identically distributed, and they come from a distribution that has a defined expectation and a finite variance, then forming this statistic here and looking at its cumulative distribution function in the limit approximates the CDF of a standard normal distribution. One can frame this also in terms of then making the step from a standard normal to a general normal distribution. State this equivalently like this. So this is what we seen here. If we look just at the sample mean, then by accounting for the fact that what we have to do to standard normal distributions to get to other normal distributions, like we've seen last time when we talked about linear transformations of random variables, then we can also write this as that the distribution of the sample mean is approximately distributed according to a normal distribution with expected value mu and variance of sigma square divided by n. We will see this again when we finally get to estimators and so on, discussing the properties of sample mean and standard deviations. If we have n and we sum these up, then we get these parameters of normal distributions. This is what we will see when we talk about the distribution of maximum likelihood estimators again. So this is what the one form of the central limit theorem based on independent and identical distributed random variables. One can generalize this to not necessarily identically distributed random variables. Why is this interesting? Because you have to think about statistical modeling from this perspective. You say, this is my theory that deterministically something like this happens. Now, in addition to what I deterministically think, a lot of other things happened. And they are independent, okay, I assume this, but they can have any distribution. Yeah? They don't need to all have the same distribution. This could be all sorts of processes that add to my deterministic model. Now, the central limit theorem, especially in this Lyapunov form, then is an analytical result that says if you have such a condition and you have all these independent error contributions, they have all forms of distributions with certain constraints. So the third central moment here actually needs to be finite. And this needs to converge to 0. So there are some constraints. It cannot be quite everything, but it's fairly weak constraints. Then the distribution of these additive things that are all independent is again the normal distribution. Again, this is done by terms of this normalization to a standard normal. So can again be expressed in terms of that the sum of these xi is approximately normal, with the expectation parameter being the sum and the variance being the variances of these. And this is, I think, the best justification for the assumption of Gaussian noise in a lot of statistical models, because you say I have my deterministic aspect, and then there is noise. And for this, about this noise, I don't know anything, but I assume that the noise results from very many different processes, all of which have certain probability distributions. But if I look at their sum as it adds to my deterministic prediction, this sum will be normally distributed. So assuming Gaussian noise is somewhat validated in terms of the central limit theorem. So this is the main point of the central limit theorem. And the point here about these two different forms is to not only always use central limit theorem as a justification for Gaussian noise, but to also, for once, look into what does the central limit theorem actually say in detail. Yeah? Questions about laws of large numbers and central limit theorems? I hope I made clear why they are interesting. So again, law of large numbers, sample mean approximates expected values. Central limit theorem gives some mathematical justification for assuming Gaussian noise, yeah? Or normally distributed errors, which is the same thing. Good. We will see in the Übung, I think the Übung for this is actually quite nice, because we will first see some more variance and expectation proofs, and then the programming for this is actually to simulate the law of large numbers and the central limit theorems, so that these kind of more or less abstract things, you can actually observe them in distributions by just sampling using random number generators. Okay, then let's have a break and start at 20 past in the other room. Goodbye.